So we've been calculating the electric field associated with the solenoid, and we still have not looked at the case where we're looking outside the solenoid. And this, again, is a surprising result. So let's do our overhead view, and now we can make the solenoid a little smaller. That's the radius capital R with our B field. And now we're choosing our Faradayan loop outside the solenoid, radius R. And again, we choose our right-handed rule and our circulation direction to be consistent with that right-handed rule. Now, what happens is a lot of times, because the magnetic field B is 0 outside, that students will think, oh, the electric field has to be 0 outside. But you'll see it's not. So first off, let's just look at the area where there's flux. This is where there's magnetic flux. Recall, B is 0 outside. And now I'll apply the Faraday law, as I did inside, B dot n hat dA. And our left-hand side is just E times 2 pi r. That's the circumference of this circle. And our right-hand side, well, let's just recall, because B and n hat are in the same direction, this dot product is positive. And because B is uniform inside the solenoid, this integral is just B. Now here's the key thing. What is the area where there's flux? Naively, you might just say, oh, it's the area of the Faradayan loop, pi r, little r squared, but it's not, because the magnetic flux is only in the region where there's non-zero magnetic field, and so that's why it's pi capital R squared. And remember, from Ampere's law, we know that B is mu naught n I, and so now we get the electric field is minus mu naught n. It depends on the derivative di dt. And here we just have r squared over 2r. And that is the electric field outside the solenoid for r greater than r. Again, as we talked about this before, if I were to put a conducting ring out here, so that's a conducting ring, and this is outside the solenoid, there is changing magnetic flux, and here, because di dt is positive, E is negative, and in this conducting ring, there would be an induced electric field, and that would drive the charges in the ring to produce an induced current. And that induced current will produce magnetic flux that opposes this increasing magnetic flux inside this whole area. And so that's our example where we're calculating the induced field in terms of Faraday's law.